with the rectangular coordinate system? What's the rectangular coordinate system? Yeah, it looks like this. And we label our axes. And we label points like this. So we would call that point, what would we call that?
3, 1.
That would be 3, 1. Why do we call it 3, 1? That's how you were taught. That's right. You put the horizontal distance first, the x distance first, and you put the y distance second. 3, 1. That's called the rectangular coordinate system, and that's very nice for a lot of things, but it's not so good for other things. So we're going to introduce a new coordinate system today. And that new coordinate system is called the polar coordinate system. And the polar coordinate system looks like this. What can you tell me about the polar coordinate system? All right, we have concentric circles. And what else do we have? What are these things? They're angles measured in radians. And sometimes we will measure in degrees also. So when we mark points here, for example, I might mark this point right here. The way we label points in the polar coordinate system is we still have an ordered pair. The first number is the distance from 0. So how far is that from 0? 3? Well, let's call this 1. So we'll call that length 1, which means that length is 1.5 maybe. So we'll call this distance 1, 2, 3, 4, for example. So that one looks like it's, oh wait, no, here's 1. I missed one right there. You're right, this is 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. I missed that circle right there. All right, so this is distance 1, 2, 3. So the first number we put is the distance from 0, that's 3. And the second number we put is the angle. So what angle is that? Pi over 6. So we would call that point the point 3, pi over 6. So in polar form, instead of giving an x and a y, we give an r and a theta. What's r? The radius. That's the distance from 0. And what's theta? The angle. All right. So how about that point over there? That's what? 1, 2, 3, 4, 5. 5, 5 pi over 6. And then how about this one? Can't see the angle there. What would you call this point? That's a good question. Well, what's the distance from 0? 4. And then what's the angle? 5 pi over 3. They don't have to be. So what I mean by that is this could also be 4, instead of measuring the angle this way, and calling it 5 pi over 3, I could also measure the angle that way. What would that angle be called if I measured it that way? Negative pi over 3. All right, so there's a huge difference between polar coordinates and rectangular coordinates. In rectangular coordinates, if I give you this point and I call it 3, 1, can I call it anything else? No. The only thing I can call that point in rectangular coordinates is 3, 1. In polar coordinates, one point can be labeled two different ways. This point is 4, 5 pi over 3. It's also 4, negative pi over 3. Could you call it anything else? Probably.
Yeah, you just keep going around and around.
I could go around and around. So I could call it 4, I could go all the way around 2 pi and then add another 5 pi over 3. So what's 2 pi plus 5 pi over 3? 11 pi over 3. So I could call that the point 4, 11 pi over 3. So how many answers are there for that point? How many different ways can I label it? An infinite, because I could choose to go around 2 times and then go to 5 pi over 3. I could choose to go around backward and then go to a pi over 3. Now, to answer Grace's question, yes, we do allow this first thing to be negative. And what we mean by negative in this first coordinate is go the opposite direction. So what I mean by that is I could call the angle this angle, which is 2 pi over 3. So on 2 pi over 3, I would then want to go this direction. So this direction would be positive 4 on the angle 2 pi over 3. That direction would be negative 4. So I could also call this point negative 4, 2 pi over 3.
I don't like that one.
You don't like that one? I don't either. Personally, I like r to always be a positive number. But that is acceptable. Some people do allow r's to be negative. This means go the other way. All right, so let's try some in degrees here. People tend to like degrees a lot. Okay, so how about this point right here? This is 1, 2, 3, 4, 60 degrees. Give me some other names for that point. 4, negative 240, because you went backwards, and that would be 240. Are you sure about 240? Wouldn't it be 300? Yeah, I think so. All right, so 4, negative 300 would be a correct answer. Right, so we measured it in that direction. So if this is 60, then this one has to be 300, because 300 plus 60 gives me 360. Okay, how about another answer for that point? 4, 420. So you just went one complete revolution and then added 60 more. That works. What if I were to put that as a negative 4? What would the angle have to be? Too late, I already wrote it. It's in pen, I can't erase it. It would have to be, just look at the line, the radial line. You just come down and it has to be 240 degrees, that's all. It's not hard. Now, this point, 4, 60. What if I drew in an x-axis and a y-axis, and I wanted you to give me the x, y values? What would you do? All right, so I'm going to do this. Do it in red here so we can see it maybe. I'm going to draw a right triangle. This is X. This is Y. What can you tell me? X is 2. Why is X 2? It looks like X is 2, but maybe my line isn't perfectly straight down. I mean, it looks like 2. I agree. And it is. I'll tell you that it is. But I want a better answer for why it has to be 2. What do we know about this angle right here? It's 60 degrees. What do we know about the hypotenuse?
4.
It's 4. So if I know this angle is 60 degrees and I know the hypotenuse is 4, how could I find X? I could do the law of sines, but that's much too hard. Well, I can't do the Pythagorean theorem. To do the Pythagorean theorem, I need to know 2 sides. If I know 60 degrees, I want X, I know 4. The 30 degrees.
I don't know.
You're all making it way too hard. Cosine of 60 degrees would be X over 4.
Oh.
You're making it way too hard. So cosine of 60 degrees would be X over 4, which means X is 4 cosine of 60 degrees. And we happen to know the cosine of 60 degrees is 1/2. 4 times a half is 2. So you were right, that is 2. How would I find Y? I could use sine. Why is this not showing up well? That made it better. To find Y, we can use sine. So sine of 60 degrees is Y over 4, which means Y is 4 sine of 60 degrees. And the sine of 60 degrees happens to be 3 over 2. So that's 4 times square root of 3 over 2. That's 2 square roots of 3.
Could you also just do the Pythagorean theorem, which you have other?
I could. Once I knew that this one was 2, I could use the Pythagorean theorem. Again, I prefer not to, because I'm then using something that I figured out. I would always prefer to use information that was given to me when I can. All right, well, I think we just figured out something in general. If I give you a polar point, r comma theta, how do you find x and y? What would you do? How would you find x? Using the cosine. So cosine of theta would be x over r. In other words, x is r cosine theta. And I could do the same thing with sine. Sine of theta is y over r, which gives y is r sine theta. So, if I give you a polar point, if I give you an r comma theta, you can very easily convert it to rectangular. X is r cosine theta, y is r sine theta. All right, so give me a polar point that you like a lot. Give me an r and give me a theta. R is 3. Theta is 180 degrees. Okay. Convert to rectangular. Well, we have two little formulas. X is r cosine theta, and y is r sine theta. R is 3 cosine of 180 degrees. What's the cosine of 180 degrees? Negative 1?
No.
Negative 1? So that's 3 times negative 1, that's negative 3. And then y would be 3 sine of 180 degrees. What's the sine of 180 degrees? 0. So 3 times 0 is 0. That makes sense, doesn't it? Where would 3 comma 180 degrees be? Well, 180 degrees is that angle. So we would be a distance of 3, 1, 2, 3. But over here, if we're dealing with x's and y's, that point would be the point negative 3 comma 0. All right, give me another polar point. Give me an R number. 10. Give me an angle in radians. Just to make it interesting, how about we get out of quadrant 1? So we'll go 7 pi over 6. And again, the directions is convert to rectangular. X equals r cosine theta. That's going to be 10 times the cosine of 7 pi over 6. That's 10 times 7 pi over 6. What quadrant is that in? Not 2. 3. Why 3? Well, one answer is I looked on the picture, and 7 pi over 6 was over here in quadrant 3. Another answer would be 7 pi over 6 is just a little bit bigger than 6 pi over 6. And 6 pi over 6 is pi, so 7 pi over 6 is just a little bit bigger. It's in quadrant 3. In quadrant 3, is cosine positive or negative? Negative, so it's going to be negative. What's the reference angle for 7 pi over 6? Pi over 6. And what's the cosine of pi over 6? Root 3 over 2? Yeah? Okay. If you're sure. So it looks like my answer is negative 5 square root of 3. And then y would be r sine theta, which is going to be 10 times sine of 7 pi over 6. So that's 10 times 7 pi over 6 is in quadrant number 3 still, that hasn't changed. Is sine positive or negative in quadrant 3? That's negative. And the reference angle is still pi over 6. The sine of pi over 6 is 1/2. So we get negative 5 for y. Questions on that? All right, how about going the other way? What do I mean by going the other way? Well, what if I give you a rectangular point? Let's start with a fairly easy one. What if I give you a rectangular point, like the point 3 comma 3? How are you going to convert that to a polar point? Lou?
You find the distance between that point and 0, 0.
And how do you do that? There's two ways. There's an easy way and a hard way.
You do the easy way.
You do it the easy way. Very good. What's the easy way? You use the Pythagorean theorem. So I'm going to do pretty much the same trick here. I'm going to use this point 3 comma 3, and I'm going to draw a right triangle. This is 3, that's 3. So to find r, I can very easily use the Pythagorean theorem. So r squared is x squared plus y squared. So in this case, r squared is 9 plus 9, which is 18. So r is the square root of 18. Which is perfectly acceptable to me, but my lab tends to be very, very fussy. It does not like square root of 18. It's going to tell you to write it how? Simplify. 18 is 9 times 2, and the square root of 9 is a nice number. So when you go to do your homework on my lab, it's going to force you to write your answer as 3 square roots of 2. You'll always want your radical simplified. I personally don't care. I don't see anything wrong with square root of 18, but my lab won't like it. All right, so there's r. To find r, we use the Pythagorean theorem. R squared equals x squared plus y squared. How about theta? We're going to find the angle. I could use cosine, but to use cosine, I would have to know the hypotenuse, which I know, but I just figured it out. And again, I want to avoid using things I figured out. So give me another way. How about tangent? Tangent of theta is what? Y over x. And y over x was given information, wasn't it? So again, I would much rather use tangent here instead of cosine or sine. Could I use cosine or sine? Absolutely. But traditionally we use tangent. So tangent of theta is 3 over 3, which is 1, which means theta is what?
You wanted radians or degrees?
I'll accept either answer.
45.
45 degrees. Or you could give me pi over 4 radians. I would accept either answer. When you're doing your homework, follow the directions. Sometimes the direction says give your answers in degrees. Sometimes it says give your answers in radians. So follow whatever it asks for. All right, give me another nice rectangular point. Anybody have another nice point that they like a lot? 0, 0. All right. Let's convert the point 0, 0 into polar form. What's the point 0, 0 in polar form?
0, 0.
0, 0 still. All right, so that was an easy one. I like that one. Give me another nice point.
7, 4.
How about we make one of those two negative? We do a different quadrant. Negative 7,
4.
positive 4. All right, so negative 7, positive 4 would be over here. All right, so again, how do we find r? We use the Pythagorean theorem. This is r, this is y, this is x. So r squared is x squared plus y squared. So r squared is 49 plus 16, which is 65. So r is the square root of 65. Usually not going to get nice answers for r. That's okay. All right, then how do I find theta? Tangent. So tangent of theta is y over x, which is going to be 4 over negative 7. Then what do I do? I grab my calculator. What do I type into my calculator?
Second.
Yeah, I use tangent inverse, don't I? I'm going to use tangent inverse of 4 over negative 7. And I get negative 29.7 degrees. How do I find that in radians? I turn my calculator into radians mode and I type it in. Yeah. Because that answer is negative doesn't mean anything. Yes.
I mean, like, does it not exist or something?
No. It does exist. What it means is it's the wrong answer. Why is it the wrong answer? Where is negative 29.7 degrees? It's in quadrant 4. The calculator is giving me this angle.
Add 180.
Exactly. I have to add 180. Why do I have to add 180?
Put it in the quadrant 2.
Put it into quadrant 2. Why did my calculator give me the answer negative 29.7? Why didn't it give me the right answer? I used the tangent inverse on my calculator, didn't I? I used that arc tangent thing. When I use arc tangent, what quadrants is it arc tangent always going to give me answers in? 1 and 4. That's the way we defined arc tangent. Arc tangent's always going to give us answers in 1 and 4. So what if our original point is in quadrant 2 or in quadrant 3? It's giving us the reference angle, and we're going to have to add 180 degrees. So the right answer is theta has to be negative 29.7 degrees plus 180 degrees. $150.3. So the correct answer, final correct answer, could be written as square root of 65, comma, 150.3 degrees. So that's option number 1. Option number 1 is add 180 degrees to your angle. Another correct answer would be I could leave my angle as a negative number, which means I would be down here and then make my R negative. So that would be my other choice. Again, this is my personal preference. I prefer the R to be a positive number, so I would write R as a square root of 65, and then I would add 180 degrees. But that is another correct answer. All right, so you do need to be a little bit careful here. If your original point is in quadrant 2 or in quadrant 3, when you use this arc tangent thing, it's always going to give you the reference angle. And you're always going to add 180. If you're working in radians, you're always going to add. You would always add pi if you were working in radians. Okay? Questions on that?
So is this sort of like the reverse of the rectangle system?
It's not the reverse of the rectangular system. It's just another way of labeling points. The right question would be, why do we use the polar coordinate system? What's it good for?
Because it tells you what the rectangular coordinate system does immediately.
Which is?
The angle and the length of the line segment.
It does give you information that the rectangular coordinate does not. It gives you the length of the segment and it gives you the angle. But what's that good for? I mean, if I can always convert back and forth, what's the advantage of calling this the point square root of 65, comma 150.3 as opposed to negative 7, comma 4? Negative 7, comma 4 looks much prettier to me. You're getting close. Nope, you're getting closer though. All right, so on my calculator, I'm going to do a couple things. I'm going to go to mode, and I'm going to change to radians, because I always prefer radians. And then, down here, this is function mode. Function mode is when we use x and y. There's also what's called a polar mode. So I'm going to change my calculator to polar mode. And I'm going to go to y equals now. And notice when I go to y equals, it doesn't give me an x and a y anymore. Rather, it gives me an r and a... And I'm going to use theta. So I'm going to type in, I don't know, 3 cosine of 2 theta. And I get theta using the xy button, just like we always do. Using the x button, except now it's theta. And I'm going to draw a graph. And look at the picture you get. Kind of an interesting picture. It is a flower. In fact, it's called a 4-petal rose, is what that picture is called.
Really?
Really, I wouldn't lie to you. It's called a 4-petal rose. Can you imagine trying to write that equation using x's and y's? It would be horrible. I agree. So what is polar coordinates good for? Fancy pictures. And where do we use fancy pictures? Many of the fonts that are used are created not using rectangular coordinates. It's difficult to get curves, especially curves like that loop around on itself, in rectangular coordinates. It's hard to get equations for that. Most of the fonts and most of the graphics that are drawn on our computer are drawn using what's either called polar coordinates, which we're learning about today, or something else called parametric equations, which we'll talk about here in the future. All right, so you can get lots of interesting pictures. I don't know, give me something else you want to try. So the cosine, how about we try sine? And let's change that to a 7. Zoom in a little bit, maybe. So what would you call that? Count again, there's 7. That's a 7-petal rose. All right, how about 3e to the theta? Let's change that number here. All right, I need to change this to go to I guess I'm just going to have to zoom out. I can't get the picture that I want. All right, skip that one for now. You got a good one?
I got a good one.
All right,
Sweet flower.
what did you type in?
I think I put white on that. I did 6 cosine 8 theta, and then below that I did 10 sine 6 theta.
6 cosine 8 theta.
And then below that I did 10 sine 6 theta.
All right, so that one alone is going to give you an 8-petal rose. No, not 8, 16. That one's a 16-petal rose. And then what did you type down below?
10 sine 6 theta.
10 sine 6 theta. That's going to give you a 12-petal rose. So you get kind of a flower inside of a flower sort of deal. Okay. Three plus 3 cosine theta. What's that?
Peach.
What is it? If I turn it that way?
I think it's ghost from like
Peach or an apple.
and
Looks like a peach or an apple. It also, you can't see it now. Take the axes out. It also kind of looks like a heart. Is it stretch? All right, well that graph is called a cardioid. Kind of looks like a heart. Maybe if I make this number bigger, it'll be better. Oh. Now I made that number bigger. I made that a 3 plus 8 cosine theta. Interesting. That's called a limicon with inner loop.
what?
A limicon. Limicon. Limicon with inner loop. Why limicon with inner loop? Because it's got a loop in the middle. All right. Same thing, more or less. What if I change that to a sine? Then it rotates it. It goes up and down instead of left and right. Anyway, as I was saying, you can get all sorts of interesting pictures with all sorts of interesting looping in polar coordinates that you really can't get in rectangular coordinates easily. Awful lot of graphics used in computers are created this way, using polar coordinates rather than x and y. Questions?